Good afternoon. So I'd like to start out, as usual, by acknowledging the Cornell Atkinson Center and the Department of Biological and Environmental Engineering for sponsoring this seminar series. So today we're very fortunate to have Professor Alissa from Columbia, and she's the Lenfirst Earth Institute Professor of Climate Change and the chair of the Department of Earth and Environmental Engineering at Columbia. Alissa majored in chemical and biological engineering at the University of British Columbia as an undergrad, and she went on to graduate school at Ohio State in chemical and biomolecular engineering. Her group develops innovative technology to ensure sufficient supply of environmentally sustainable energy for humanity, and she will tell us what it does. So welcome. Thank you.
Is it loud enough? Okay, if you cannot hear me, please stop me. So coming from New York City, I brought you very warm weather, right? I was like, what's going on? It's in the end of March. But it kind of brought back memories because I think about 2009 and 2010 time, I used to have a collaboration at Cornell. And I remember each time when you come up, there'll be a very gentle snowfall over the day, and then it looks so pretty, but then it'll be very hard for me to get back home in the city. So it's great to be back and great to see such a large class. And I guess all of you are very interested in climate change and how to fix it, right? So hopefully I can tell you what a lot of us working on, how to address climate change, working with the environment. So hopefully you will get some story behind that. So the title I said is Towards Sustainable Energy and Materials, and you will hear about how materials comes into sustainable energy and climate change mitigation. And with the focus on, I'm going to call it carbon capture, utilization, and storage. How many of you heard about CCS or CCUS acronym? Good. So we have a good background in that information then. So I think in the United States, we've been working on CCS and CCUS about 3 decades, very intensively. I think a lot of advances has happened over the years, but it was about 2013 and 2014 time, people start to get quite frustrated. Because if you're in chemical engineering, you learn that some technology from your brain thinking of concept all the way to the commercialization takes about 2 decades. Sounds right, especially large-scale systems. But then we've been working on it at least 2 decades by the time this happened, these reports. So people are getting confused. Well, we worked on it for 2 decades. Why don't we have them working in the industry? So when IPCC and national academics started writing this report, people were a little scared. Are we going to give up? Is this just too difficult? And even this is quite a long time ago for you guys, I guess, when you're little. So when 2013, this report came out, we were really scared that, well, we don't want to give up, or maybe people would be interested in giving up and do something totally different. And then this report said this: we need substantial multi-century climate change commitment created by past, present, and future emissions of CO2. Interesting, right? It doesn't seem like a really scary statement, doesn't it? It seems to be very simple, right? Basically, they're saying CO2 is a problem, carbon dioxide. We're going to do something so that we'll eliminate the present and future emissions of carbon dioxide. Sure, that's what we call it, zero emission, right? There's some positive emission, we're going to go to zero. But then we were quite surprised with this short statement because of this. What happened to the CO2 we historically emitted? Do you see one here? Maybe, right? They're being mixed into atmosphere and they stay in atmosphere really long time. So we kind of diluted carbon dioxide into our environment in atmosphere, although we complain about the high concentration or total amount of carbon dioxide in atmosphere, but that's still 415 ppm, parts per million. So in order for us to go back into the history and pick up the CO2 we emitted in the past, it's really a big challenge. And that's when we start talking about, we need to not only have zero emission, we need to do negative emission technologies. It's good, right? Because we are saying we're not shy, we can do this, and we're committed to do this. So with this, they realized that this is not can be done with the one technology, and it cannot be done with the one group of researchers, or not even a one country. So some of you may have heard about mission innovation. How many of you? It's been a while already. It was after the 2013 report, 2015, there was a Paris Agreement. Some of you may heard about. We just had a COP26 last year, and this was the COP21. And at the time, all the countries in the world got together and said, this is such a big problem, and without agreeing with each other, and we are really committed to do this, it'll be very hard to make a dent in climate change. So what 22 countries in EU, basically the entire country, got together and decided was, there are many things we need to do to get to net zero or negative emissions. And in order to really address climate change, it's not going to be single technology. So they came up with 7 buckets of technologies we really need to focus on. And then a year later, we added one more called hydrogen. And you can recognize some of these buckets. So how about smart grid? You guys heard of that, right? How about sustainable biofuels? Yeah, we do a lot of research at Cornell about that, right? And third bucket was CCUS. And when you look at all these, they're kind of written kind of siloed way, but they are quite interconnected when you think about it. So for example, we can convert the sunlight and make hydrogen, or using sunlight or clean energy materials to make more sunlight. So not understanding how they're synergistically connected to each other and how all these solutions has to work with each other, we can really make a dent in climate change. In addition to that, it was a very interesting meeting at COP21 because the mission innovation people got together. It was a ministry of all the countries got together and said, when we talk about the climate change mitigation, unfortunately, it's not going to be solved in 10 years or 20 years. Sometimes people talk about these as a bridging technology or bridge, right? But this bridge is going to be so long that it will take entire year generation and more, possibly. So when you think about it, remember I just told you that in order to have a chemical process, for example, come from your concept all the way to commercialization takes about 2 decades. So if I ask you, do we know which technology we're going to use in CCUS in 2030? Right now it's 2022, right? More likely we know what we're going to build in 2030. How about 2050? What 2100? We don't know, right? Because the science will advance and technology will advance. Hopefully we're not going to have the same system, same as today in 2100. So what they did, amazingly, in my opinion, almost first time in the history, all the countries got together and said, wow, not only we need to learn how to deploy the technology we already have, we need to really advance fundamental science and engineering and policy to get there. Because we don't even know what technology we're going to use in 2050 and 2100. So basically they got together and they created all this roadmap or kind of vision statement and said, let's advance fundamental science and engineering for doubling up our funding and then really emphasize what we need to learn and what we need to discover for the future. It kind of tied to what's been happening in the United States. How many of you know Department of Energy? Some of you hear about all the news about how they set the direction on how our energy infrastructure will be developing in the United States. Also, what future research and technology development is going to happen in the United States. Within Department of Energy, we have a fossil energy office. And this office been doing a lot of research on how to make clean energy in the United States. And interestingly, last year, they changed their name. I think that some people really wanted to get rid of the fossil energy altogether from the name, but they couldn't. So what they did was that they added something to it. So now name is Fossil Energy and Carbon Management. Interesting, right? I think this tells you something. If you look at the history of humanity compared to history of the Earth, we're a little blip, right? Last 22 seconds or something, very tiny. But if you look around, we have amazing things we use and enjoy and utilize. And this all happened because we discovered high energy density fossil materials, fossil resources. And there's nothing wrong with coal or methane. These are just materials which was embedded in Earth. Which is the way we utilize them over the years was not considering the environment within the system boundary. But they were great because they had such a high energy density. So now looking into the future, we understand we still need carbon. So if we can somehow manage carbon better, maybe we can approach the clean energy systems at the same time, mitigating climate change. I think it's at least a good direction to go, even at the government level. And there are much more fun stuff happened last year, and this is one of them. How many of you heard about energy earth shot? Nobody? Oh no, they should be a little more communicative to general public and I guess students as well. So we have somebody called Secretary of Energy in the US government. And basically this person really kind of governs and leads the effort on which direction of the future energy we should go in within the United States. So our Secretary of Energy, Greenholm, and she announced something called Energy Earthshot. And this is a way before your time. Maybe you remember, and I kind of remember when I was little, I guess, moonshot, right? Any of you know moonshot? Go? Yeah, some of you, right? Maybe you read in the history book. So in the United States, they just said, we're gonna go to the moon no matter what it costs. That was a moonshot project, right? Now they call this, modeled after that, they call it energy earthshot, meaning that they're saying, this is such an important thing, we're gonna do whatever it takes, we're not gonna stop until we get there. Isn't it really cool, right? We have this mission and we're gonna all work with each other. Nothing to do with the discipline, nothing to do with where you're coming from, but everybody's thinking that this mission is so important. So far, there are a number of them already announced. So first one was announced in June last year, 2021. This was on hydrogen. So hydrogen energy earthshot, the goal was, we want to get to $1 per kilogram of hydrogen in 1 decade. It's a very ambitious goal. And this was because our ultimate goal is net zero economy by 2050. They're saying we don't want to be hungry, we don't want to stop flying, we don't want to stop not using electricity, but while we are doing what we do, still we want to go to net zero by 2050. Very ambitious goal. There are a few others. Second one was on long duration energy storage. Third one was quite relevant to what I'm going to talk about today. So it was carbon negative earthshot that was announced in November. Again, hoping that we're going to achieve net zero emission by 2050 by developing CCUS technology at $100 per ton of CO2. Again, this is very ambitious goal. So looking at all these, you can see this is the big mission we have. Like we went to the moon. Hopefully we'll make it so that we can save the environment at the same time. We can provide affordable energy to all mankind. So what have been doing so far? Carbon capture, utilization, and storage. Let's talk about capturing that first. So what do you know about carbon dioxide? I think you talked about a little bit in the class, right? Carbon dioxide is acidic gas. So if you want to do reaction and capture it, what would you need? Acid, base, and then put together, it neutralizes itself, right? So if you want to capture any acidic material, you want to have a base. So people knew that, or you can physically separate them, and there are many different ways. So I'm not going to go through all the technology out here, but this is like how far into the future they can be commercialized versus cost reduction benefit. So obviously, some of these systems are much easier to do, and you can actually do it today. So one of the things is, if you want to capture CO2 by using acid-base reaction, you can have very strong base, like a sodium hydroxide solution right here in a cup. then you will absorb the CO2 from atmosphere even at low concentration, because strong base really are very reactive. So you can capture CO2 very efficiently. But then they go downhill so much that you're not going to use this liquid only once and throw it away, right? Because every material you have, everything has carbon footprint. So if you capture CO2 once and throw it away, that doesn't make sense in terms of net CO2 benefit. So a lot of these CO2 capture materials, you have to do catch and release and catch and release until you get the pure CO2 comes out. So whenever there's a really strong binding energy, like a strong base, you can do capture very easily, but now you have to go up the hill a lot more. So the energy you have to put into the solvent regeneration reactor is really huge. On the other hand, if you have really weak base, it doesn't have a big binding energy, then your capture reactor will have hard time because it's not a strong pull. But then during the regeneration, you just need to put a little bit of energy. So people have been looking for what is the optimum binding energy. And then they found that things like amine, which is the base, which is good enough to capture CO2, but not too strong, so that with the moderate amount of energy, we should be able to regenerate this material. So a lot of people worked on this area. And in fact, we went all the way to not full commercial scale, but almost near it. So this is the picture of Petronova project in Houston. And this is actually a photo I took with my iPhone. Pretty cool, right? I get really excited to looking at shiny reactors. So this one is CO2 capture tower. This is the solvent regeneration tower. You can see a person will be about this small. This is not even a full scale. So this is the reason it takes about 2 decades, because you cannot go from beaker all the way to this scale right away. You have to do a lot of scale up, understand what's the challenge going from tiny reactor all the way to full scale. The reaction is very different, mixing is very different, mass transfer very different. That's why we had to do a lot of learning in these large scale systems. Unfortunately, this system stopped working. We stopped doing this project in 2020. One of the reasons was they capture CO2 and release in pure form, and they were selling that CO2 for enhanced oil recovery. But because oil price fluctuation is started to make less sense in an economic way, so they kind of stopped. But this is a very important milestone project in the United States, because more large-scale demonstration we do, we'll be able to learn more, so the next plant each time will be much better and much more improved. Having said that, people estimated something like this, amine-based liquid, like a water-based system, will have huge parasitic energy consumption. Because if you go back to this reactor scheme, we do CO2 capture at about 40 to 60 degrees C in the power plant. And remember, I told you we need to put energy in to go back up and then release the CO2, right? And easiest way to put energy into something is by heating it up, right? By heating it up, the material provide the energy. So this reactor usually run at 120 to 140 degrees C. And what happened was they wanted to use amine, which captures CO2, but something like a monoethanol amine, they cannot work as a pure form. So they usually dilute it into water. So maximum concentration in this solution is about 30 weight percent. So what's the rest of it? Water, right? So what they have to do is that the 30 weight percent solution goes to CO2 capture reactor. And then after loading CO2, you pump it to the next reactor and then provide heat and then release CO2. And then now CO2 lean solvent goes back. So there's a lot of circular motion going back and forth, right? So you have to heat up very fast, cool it very fast. Otherwise your reactor will be really big. So water is not doing much other than diluting things in this case, right? And I guess some of you do cook, right? I don't cook much, but at least I make tea and coffee. And it takes quite a long time to boil water, right? Because the heat capacity of water is really high. So imagine heating all that water, 120, 140, then you have to cooling it down to 40 to 60 very fast, all the time. That increases energy consumption for CO2 capture system for long time. So this is one of the major reasons. I think we're getting to solve that issue by doing very innovative heat integration. And we're trying to make new solvent systems, doesn't really require a lot of water. That's another direction a lot of people went to. So speaking of that, here are some of the examples of waterless and water-amine solvent. We still like that amine functional group reacts really well with carbon dioxide. That we want to keep. But we just wanted to get rid of water, which is just coming along the ride more than anything and consumes a lot of energy being heated up and cooled down. So I'm not going to go through too many of all this chemistry, assuming that you didn't take organic chemistry yet, right? So this is ionic liquid, and it's like a molten salt under room temperature or below 100 degrees C. And then cobalt, these are developed by Pacific Northwest National Lab. It's like a switchable solvents. But there's something called NOMS, nanoparticle organic hybrid materials. And this is the particular material I've been working on last little over a decade or so. And I can totally blame to your dean that I'm working on this because about 2009, Lyndon Archer, engineering dean, called me and said, Alissa, I made this really unique material. It's very similar behavior as ionic liquid, which I really liked. But then it's very easy to make, and there's a lot more tunability for both chemistries and structure. So I got really intrigued. One of the reasons people really like ionic liquid, top left, is because it doesn't have vapor pressure, which means when you boil water, what happens? As you heat up the temperature, you see steam coming up, right? Because it has high vapor pressure. But ionic liquid, you can heat it up to hundreds of degrees and has no fume comes up. So that's nice because when you do a lot of designing reactors, you don't lose your liquid solvents to something, right? It stays intact in your reactors. And it's quite robust that you can do a lot of temperature swings and you won't degrade, which is very important. So I got super excited. So we started looking into this. The way Lyndon was designing this NOMS material was, at the end of the day, it still behaves like a liquid. If you make it, it looks like honey-like consistency. It's a viscous fluid, but still fluid, not a solid. But you start with a nanoparticle, which is solid, and we tether the polymer, right grafting density and right size, and we were able to make liquid-like material with this hybrid system. And because we can functionalize all these polymers with the functional groups you like doing certain tasks, we were able to tune this chemistry quite well. But another thing we kind of hypothesized was these materials, similar to ionic liquid, will have great thermal stability because we need to do a lot of temperature swing, which should be thousands and thousands cycles. So first generation of NOMS we made for CO2 capture application, I think Lyndon did a lot of work on batteries, NOMS-based batteries. But in our group, we were working on CO2 capture materials. First we did was compared untethered polymer with polymer tethered onto nanoparticles. And we were very curious whether it would change its thermal behavior. And we saw that the window of stability increased almost like beyond 100 degrees. That's really fantastic. But it's not once. We tried up to 100 cycles. And as you can see, the NOM sustains really well compared to untethered polymer, which we started with degraded. So if we use both this material and this material has the same power to capture CO2. But after 100 cycles, I have only 20% of this left. This is not going to be economical. Not only this is not economical, environmentally, where rest of the polymer goes, right? More likely, a lot of emissions. So we start thinking that, wow, this is great because NOM seems to be intact and then maybe we can do a multiple thousand cycle and catch and release of this carbon dioxide. But one of the things we were also interested in fundamentally was, if you look at the structure of NOMS, these are the hairy nanoparticle with certain distance between polymer chains. And what we thought was, as we make this material, if we can get rid of all the water, then as these fluid units get closer and closer to each other, now this polymer chain has to really stretch to fill up the gap between nanoparticles. And if we really make them stressed out, then you will love to absorb the small molecules like carbon dioxide and then relax them. So we wanted to test that hypothesis. So this is a 2D ROSY NMR, basically showing that what is the form or structure of these polymers attached to or tethered onto nanoparticle or untethered one. So without going through NMR analysis, this plot is untethered polymer versus this is tethered polymer. And you see a lot less signal in here, right? Basically, this tells you that the tangled polymer compared to the tethered polymer onto our NOMS material was stretched out and stretched out from each other. So what we found out was by doing so, we created a lot of something called free volume between polymer chains so that we were able to jam pack CO2 a lot more differently and also had a better accessibility of all the functional groups we wanted to have between. So the only thing we had to do now was we just need to decorate all these polymer chains with amine, which loves to grab on CO2. And that's what we did. So as you can see, each time we add more amine functional groups along the polymer chains, we got much more CO2 loading per gram of the material, as expected. So up to here, we were super excited about the data. Wow, we can make these novel materials, very robust, 100 cycles. We can load up a lot of CO2, no problem. But this is still when we are making very small amount of material, doing all the fancy characterizations, understanding structure and chemistry. But then now, remember that huge reactor? I need to somehow make enough material to go into that reactor and moving them around, right? Remember green reactor, red reactor, going back and forth. So then we start making more and then start looking at, how are we gonna move them around? So we start looking at the viscosity first. So if you look at the viscosity, you know what viscosity means, right? Water is low viscosity so that you can flow things. Like if you have 2 cups back and forth, easy. But if you have to do honey, it's harder, right? Because it's highly viscous. So this is where amine-based water-like solution is very low viscosity. That's why they can do all kinds of easy reactor design. Mass transfer is not an issue. Heat transfer is not an issue. But second level is like the red dots and cross dots. That's ionic liquids. So you can see they're higher viscosity, right? And then the top level, some of the groups at the top, those are the NOMS material with viscosity super duper high. And if you look at the plot, if some of you noticed, what is the y-axis? It's not even linear, right? Peter is laughing because it's a log plot. So as soon as I saw this, oh no, this is not good, right? It's extremely viscous, which means that we'll have a really hard time, 2 things. First, even moving this material from one reactor to the other reactor would be very hard. Like it's moving like a honey from one place to the other. Second, when you try to capture CO2, CO2 is in the gas phase, and this is the liquid phase. Without having interfacial area, you cannot capture CO2 because it goes through interface. Creating interface in low viscosity fluid is very easy. You can make droplets, you can do all kinds of things. But if you have really high viscosity material, it's really hard to create interfaces. So we started thinking about this. Okay, should I give up on this material? Although it's really interesting. In fact, my friends in Ionic Liquid, they were kind of in the intermediate range. And they go, hey, we can do this. We can lower the viscosity down to 40 centipoise. We can do this. So they actually worked on it for a long time. But I was looking at our material and go, well, this is way too high. But then I started going back to why we were concerned about viscosity. So somehow, if I have this sticky fluid, if I can somehow chop them apart and package them separately, maybe it's okay, right? So some challenges becomes opportunity. So there are different ways to handle this. And today I'm going to tell you about encapsulation, but we also changed the hydrogen bonding network and all this more chemistry to lower the viscosity. But let me tell you about encapsulation, because that's where I got really excited about this. So what we did was, in order to separate them and package them separately, we developed this microfluidic device. And this microfluidic device, what we did was we created a droplet inside a droplet. So blue here is, let's say, for example, any high viscous fluid like NOMS. And then white fluid surrounding on the top left is UV curable polymer. So now you have a droplet inside a droplet we created, and then I UV cure only the white part, which is the shell. And what you really want is the shell is gas permeable, right? Then gas can go in, being captured. And now you have a lot of surface area. And we were able to make them. So these are the actual photos of our materials we made. So these are micro beads. It's about 300 micron. And you can control the size depending on how much interfaces you want to make. And now instead of dealing with honey-like sticky fluid, you have particles to deal with. Now your reactor design can become a lot more flexible and you don't need to worry about mass transfer as much. We can make a multi-core, single core, many of these. And as we expected, compared to norms we started with right here, you have a huge improvement in how fast CO2 being uptake by same amount of materials. So comparing red versus black, encapsulated system now have a much faster reaction rate, means that your reactor size will be a lot smaller. And you don't need to use as much material. But then now looking at this, even this much mass transfer, I start thinking that, oh, maybe we can even improve even further. Because compared to bottom one and top one, which one has higher interfacial area? Top one, right? So then maybe we can push even further down that direction. So we made something called SIPs. This is solvent impregnated polymers, we call it. And how we prepare this is that with the UV cured polymer, instead of making droplet inside a droplet, we basically mixed our gnomes and then using really high shear, create a micro immersion. And then we UV cured. Cool, right? So then now you have a very, very sub-micron droplets inside UV curable polymer, which is gas permeable. So this is when right after we did the high shearing mixing, creating all these micro droplets, you can see some of the droplets and then going from top to bottom, is the top has only about 9.8 weight percent gnomes and all the way to 49% gnomes. And as you can see, it's almost like a well-mixed fluid system. And then we did the UV curing. And it looks like it's so well mixed, you don't even see gnomes, right? The little droplets anymore. But we wanted to make sure they're well integrated. So this is SCM image with the nitrogen mapping. Nitrogen shows you where gnomes are. And as you can see, there's a different concentration and it's well distributed. And by using this material, this is the kinetic difference. If you use gnomes without anything, you will continue, but very, very slowly because uptake rate is very slow. But using SIPs, we were able to really boost up how fast this material can capture CO2. So I think a lot of people are now looking at how to combine reaction rate and mass transfer so that you can design a hybrid novel materials to do CO2 capture a lot faster. So what would you do once you capture CO2? That's another big question, right? So if you really care about the climate itself, we have to store, unfortunately, because it means that, remember, zero emission versus a negative emission? In order for something to be called negative, you have to see the change in CO2 concentration in atmosphere. If that is negative direction, that's good. In order to really do that, you have to take CO2, either positive or from air or from environment, and putting it back into the ground. So in order to do that, we need to do carbon storage. That's given if you really care about climate change mitigation today. Once we fully decarbonize our power sector, maybe things can change, but not today. So there are many different pockets in geological formations you can inject carbon dioxide. Because you cannot build a large enough storage tank, we had to go to the environment and looking at all these pockets of spaces, pore space we can tap into. And this is one of the very famous Sally Benson sketch or schematic, is that what happens to the carbon dioxide once you inject into the geological formation. So this is time versus the different trapping contribution, means that first you need to find the reservoir because this is the storage tank, right? If storage tank is open to the air, it's not a storage tank, right? Because it's a gas, it can go out of this tank. So you need to make sure that there's a lid. And that lid is called cap rock. You need to find a cap rock which is not permeable so that gas can be contained within your storage tanks, which is a geological formation and reservoirs or aquifers. So people found this in different areas and pockets and they start injecting CO2. First, you will stay as a CO2 plume and a big bubble. But then we inject CO2 at about 150 atmospheric pressure, which is huge pressure. So we start going into the pore spaces slowly into that. But pore spaces are not empty, right? It's usually filled with the groundwater. And this groundwater will be replaced by CO2 bubble. That's the second stage called residual CO2 trapping. And then as time goes, there's a thin layer of water surrounding this CO2 bubble. Now CO2 start to dissolve into that water layer. That's called solubility trapping or ionic trapping. Finally, only if there's a geological formation is highly reactive, then you start to form mineral trapping, which is, it actually makes like an artificial limestone in situ and becomes solids. So this is the sequence. And interestingly, there's no number on the x-axis, right? So the biggest question was, how long would it take each of these steps to happen? Because depending on where you are, the risk and what's happening, fate of the CO2 is so different. So people really wanted to know. If we inject CO2 in this site versus that site, on other site, what would happen? But we haven't done a lot of experiments with our Earth yet. So last one, mineral trapping, we worked a lot in my research group, as well as Professor Garikoda at Cornell doing a lot of research in because of this thermodynamic downhill. Compared to many of these trapping methods, the carbon mineralization is the most stable in a sense. Look at it, right? You start from coal or natural gas way at the top, and by burning it or using it, you're making carbon dioxide. That's a downhill in thermal, right? This is the reason we are recovering that energy to use. We make it electricity, we do other things. But one more down step is making solid carbonates. So once you have a limestone, for example, unless you burn limestone, CO2 will not come out. Burning limestone is going uphill, right? Making carbon dioxide. So we got super excited about this, but we weren't sure whether it will take within our lifetime, right? Because we want to make a dent on climate change within decades, not millions of years. So this was a very interesting experiment they did in Iceland. And in Iceland, they have very interesting geological formation, but not only that, they had very interesting system of geothermal energy system. So they were already injecting a lot of water into a geothermal well, and then taking all the fluid out, and then that fluid came out with a lot of carbon dioxide. They said, well, we have a geological sequestration potential. We have all this CO2 coming out of the well. Why don't we re-inject back into the basalt and then see what happens? Because it's really highly porous. And we were really curious whether it will convert into the solids. And it would be great if it can be done within a couple of years or even tens of years. But how do we know if you drill and then find the limestone-like material, solid carbonates, how do you know that's the carbonate we formed? Because the limestone is everywhere in geological formation. So I was involved in this interesting experiment. What we did was we wanted to tag carbon dioxide we inject underground with something both either non-reacting or reacting. By looking at the difference, maybe we can tell which one was the carbon actually converted, the one we injected. So we sent in two tracers. One is SF6, which is non-reacting. The other one was CO2, which is radioactive. So it was carbon 14 instead of 12. So if you burn coal, you get only carbon 12 because it's an old carbon, it's dead carbon. So there's no radioactivity you need to worry about. But if you burn biomass, it has a 1 parts per trillion carbon 14. Because in air, live air, we have about 1 parts per trillion carbon 14. Interesting, right? So if we have carbon 14, that amount, most of the carbonates in geological formation formed many years ago should have 0 carbon 14. But new one, which we spiked with the carbon 14, we should see that. So we checked, and then we saw that all the SF6 came back, but not the carbon 14. So we got super excited. Maybe we did form something. And in fact, this is a really famous photo. They drilled, this is one of the core, they got it out of the Iceland, and you see that these are like crystals, and then they got super excited, and oh, we formed carbonates. And later I was told that that wasn't the carbonate we formed, but they did find it eventually. But somehow or other, we're still using this photo. But it was interesting to see that this formation actually made carbonates within 2 years or less. So maybe it's possible we can do this. So how fast can we get there, making an impact in climate change or making the change in how we view environment, also using our energy resources? This is the kind of a projection published in 2020, I believe, by McKinsey. And if you look at these different color bubbles, the light gray bubble is that what is the carbon storage potential by 2030? I really hope this is underestimation. I hope this light gray bubble is as big as possible, because that means we're really doing something for climate change mitigation. But you also see these bigger bubbles, which has a fuel, construction, biochar, and many other things, right? So what does that mean? Basically, that's what they anticipated. Once you have captured CO2, we can even make stuff. We call it carbon conversion or carbon utilization. So for example, let's look at the construction. That's a pretty big bubble, right? They're saying that's quite a big bubble by 2030. Maybe we can use building materials using carbon dioxide. In fact, United States already discussed it about 10 years ago. About 2010, we start thinking about if we have captured CO2, can we make stuff? Right? These are some other things they said they can make or use. So for example, I think some of them, you guys drink soda, right? We can make soda apparently. Fire extinguisher, or fertilizer, chemicals, and all that so on. Obviously, the size of the bubble doesn't correspond to the market size or climate change benefit. But basically, this is saying that once you have carbon captured, there are potential you can make a lot of stuff. But if you look at a lot of these, which I'm going to talk about later on, that it's energy uphill most of the time, except again, going downhill using carbonates. And another push for this direction was not only there's natural materials you can convert into carbonates, but there are a lot of industrial materials you can convert into carbonates. So these are steel slag, red mud, or fly ash, or these are solid waste from industries. And interestingly, these industries are also have a huge point source of carbon dioxide. Okay, so I have acidic gas as a waste. I also have basic solid as a waste. I landfill one, I emit another one. Hey, why should we do that, right? If we can somehow figure it out, put them together, and maybe we can produce even products, maybe that's not a bad thing. So a lot of people start looking into how to decarbonize, for example, power plant using fly ash, or iron and steel industry using steel slag. And there's a lot of research going on in this area. One of the challenges of carbon mineralization is this. A lot of materials are either silicate materials or complex materials doesn't really dissolve, gives out calcium and magnesium entirely. So there's a residual solids and all that, so that in a sense that your dissolution has to happen at low pH, but then carbonate, the solid formation is favored at really high pH. So if you do really low pH dissolution and really high pH carbonation formation, it works great. But remember I was telling you that every chemical, every material has carbon footprint. So the more we use it, overall net system may not be carbon negative, right? Maybe it's not beneficial. So there's a lot of research going on how to reduce, narrow down that gap so that mild acid base, like a pH swing with a much smaller window. So there's a lot of research going into this area. But good thing is, once you make the solids, now we start putting into concrete, and it works really well. So one of the reasons concrete has high carbon footprint is because cementitious material, which is like a glue within the concrete, has high carbon footprint. We were able to replace these materials by 30%, 38% of this material with our newly CO2 utilized materials and lower the carbon footprint of building materials. In fact, in Colombia, we developed this technology so that if you look at the top left, this is a current technology. Iron and steel industry make a lot of CO2 in flue gas. They also make a lot of solid waste, and they have a lot of waste heat. We keep calling them waste, but it has stuff in it, right? So we start looking at them as, instead of waste, maybe they're unconventional resources. So if you look at the right-hand side, we actually use all three of those and make construction materials. And this big white chunk stuff is the white calcium carbonate. We put it into concrete. And at the same time, we found that there's other things in iron and steel slag, so that we were able to even recover critical elements and rare earth elements out of these feedstock. So in the picture which I took in China, this is about to steel. It's about, in terms of size, about 13, 15. It's not the biggest iron and steel plant. These are the piles of, maybe this is the truck, so a person will be about this size. They're piling these slags like a mountain tall, like really, really tall. And have you been to New York City? This is not even a big company. And they're filling up, have you been to Tribeca in New York City? They're filling up 1/3 of Tribeca every 4 years. This is a big problem already to start with because solid waste, but now we are looking at how to fix carbon dioxide making artificial limestone. So this is another way to do it. And I think this leads to very interesting discussion on infrastructure, because you see carbon everywhere in the buildings. So right now we have only single direction: mine the material and make the construction material and done. Can we somehow putting it back so that we have a circular economy of all these solids? It'd be great. But it's not easy, because once you make into complex system, making into feedstock again takes a lot of energy, especially a lot of acid and base. So now huge push in this area is now, instead of having heat, like from fossil energy, if we have only renewable energy. Renewable energy is not in the form of heat, right? Usually in the form of electricity. So how to electrify chemical processes became a big challenge. So for example, using renewable energy, we can split the water into acid and base. So by doing so, now we can create a whole new way of making even construction materials. Okay, going back to these bubbles again, because there are other big bubbles as well, like fuels and plastics and polymers. So this is where I'm from. Although this is the picture, look really pretty. In fact, Colombia is not near here, it's way up north over there. But still, you can see in the city, there's a lot of materials. And we use a lot of chemicals as well. And these are the common chemicals you see a lot. Let's look around this room. If I ask you to point one material does not have carbon in it, can you point it out? Okay, who's gonna find it first? Anything without carbon? No, it's hard to find, right? If you have a bottle of water, water might be without carbon, maybe, but most of it, including humans, we have carbon. So can we decarbonize cities, chemicals? No, without carbon, there's nothing, right? It'll be just hydrogen and oxygen and maybe other things, which is challenging. So what we start calling, I started using this term about 4 years ago. And at the beginning, my colleagues in industry say, don't say that. But now we are using it. So instead of decarbonization, we have to say defossilization. This basically means that we're okay with carbon. Carbon is not a bad thing, right? As long as that carbon is not attached to fossil, then we'll be okay. So let's think about this a little bit. If we can have new circular carbon economy, which means that I still want you to have a great life and being able to use materials and chemicals and then do all that, but eventually you will end up somewhere. It could be in the environment, it could be somewhere, but can we create the circularity with only input into this bubble should be renewable energy and hydrogen, right? Because this is for carbon. So, but we still need hydrogen. If it is only CO2, there's only carbon and oxygen, no hydrogen. So in order to make stuff and fuels and materials, we do need hydrogen. And we'll talk about the problem with hydrogen later. But because of this, remember I was telling you about energy earthshot, hydrogen and carbon, they're really interconnected in terms of discussion. And once we have it, somehow if we can capture CO2 and convert to upgraded high-value materials, if we can understand how to put this into tech to market, but we also need to understand economics and policy, how it drives the entire transformation, that's very, very important. So people start looking into this. So if I have to ask you, we cannot use fossil carbon for any of these, where would you get your carbon? This is a really important problem for your generation. If you are willing to stop using petroleum, coal, and natural gas even, where would you get carbon? Well, carbon is in many different forms. Let's do gas, liquid, solid. Gas is air, liquid is ocean, solid is limestone. Hopefully, let's not worry about limestone. Let's not use that because it's already well stored, which means that we have to go back to the environment, right? We can go directly to air or oceans, and then you can harvest carbon. Or if you want to go through biological route, you can go through terrestrial or marine biomass. Either way, the carbon came from the environment, which is non-fossil. Great, right? If we can somehow create the entire value chain and chemical industry based on this, this will be really truly defossilized system. So I'm sure it's tough, right? Compared to mining petroleum or coal or natural gas. So let me give you an example of direct air capture. You can actually do terrestrial biomass, which is fixing CO2 into biological form, or you can do that chemically by directly capturing CO2 from air. Obviously, this is not an easy task, but there are a lot of companies did pretty well on this. So if you look at the system on the top left, this is the kind of modular design, and each module is about my height, I think, when I went to visit. So these are the modular design kind of stack on top of each other, and all these fans are moving air through. Because remember, it's only 415 parts per million. You're fishing in the river with a very small number of fish. So in order to fish enough fish, you need to access huge amount of river, right? Same thing for air. So you have to process a lot of air through this system, and then you have to capture CO2 at very low concentration. And because of that, it's really hard to catch all the carbon dioxide from the air. So our target is not like point source capture in the power plant, like trying to capture over 90, 95%. As long as you can catch more than 60% of CO2, you're good. And there are other challenges compared to power plants. Because CO2 concentration in power plant is about 10 to 15 volume percent. If you're burning natural gas, maybe 5 to 7%. Now you have to worry about many other things because you have to move so much air that you don't want to have high pressure drop because it's impossible to compress all the air and then push it through because it would take too much energy. Another thing is that like some days are rainy days, some days are snowy day, high temperature, low temperature fluctuation. Most of your reactor systems are well controlled, but not this one, right? Because your reactant is coming, incoming stream is always changing in terms of the temperature, concentrations, the dust level, and on top, it has a high concentration of oxygen. And oxygen is quite not good for a lot of materials because it has a much worse for the thermal stability. It likes to degrade things when you have high concentration. So we start looking into our materials. Can we actually use this material we developed for point source capture to be used for direct air capture? And we were able to, which is kind of nice. So this is comparing thermal stability under nitrogen condition versus air condition. So this is the one with a huge 21% oxygen. That one is almost zero. It's a zero oxygen condition. And the dotted line is the pure polymer. And then the solid line is our nodes, comparing back to what we developed. And if you look at it, in the nitrogen condition, the untethered polymer was doing pretty well. But as soon as we put the oxygen into the system, they start to degrade very quickly. So do you remember after 100 cycle, it had 80% degradation? This is one of the reasons. And if we actually calculate the activation energy, it's really clear. So on the left-hand side is untethered polymer. There's a big difference difference between activation energy under nitrogen condition versus air condition. It takes so little energy to degrade polymer under oxygen condition. At the same time, if you tether them onto nanoparticle, it maintains. And that one of the reasons, or two of the reasons they work really well is on the left-hand side is untethered polymer, on the right-hand side, this is our gnome system. And because of the increased viscosity, oxygen could not really penetrate through all these systems. And we had a lot more stabilization of the different functional groups because of the tethering. So we got super excited because we can actually sustain the red bars or gnomes up to 20 cycles, worked really well compared to, again, polymers start to degrade each time when we try to capture CO2, even directly from air. So then we start thinking about, well, we like it, but can we even go faster and then somehow lower the pressure drop even further for CO2 capture? And that's when I started talking to Professor Yong-Ju in chemical engineering at Cornell. Because he has this electroscreening device and very unique one with the gas assisted. And he said, yeah, I can make something like here, like furnace filter. Furnace filter in your house runs the air in the house very easily without having too much energy to pass through, right? So I thought, well, this is really clever. If I can load up a lot of gnomes material or anything really loves CO2, maybe we can create this, even capture CO2 from building, but even outside. But one thing is, in order to make this electrospin fiber, we need to have a fiber material, not only CO2 capturing active material. Remember that our active material is sticky and it grabs onto all the dust and all that. We don't want that. So then we worked with Michelle Kidder at Oak Ridge National Lab, and she had a very interesting polymer, has really big porosity. So we started putting these together, and then maybe we can make a material capture CO2 very well. So first we started something called PIMS. This is the polymer with intrinsic microporosity. It supposedly have a high surface area. So if you look at the BP surface area, it's a 700, almost 50 square meter per gram, which is huge. Trust me, it's a high number. It means that not only there is a surface on the fiber, right? But internally, it's like a sponge-like. There's so much area you can access to. And then it means that as not only this filter-like material has low pressure drop, on the surface of this fiber, CO2 will go through and then being grabbed by gnomes very easily. It was really exciting, but another thing I was super excited about was this. Because all the fluorine groups and also aromatic rings, they became very hydrophobic, which means that if you have a dust on the surface and all that, maybe we can wash it up very easily. And another challenge of a CO2 capture directly from air is that not only it has a CO2 capture challenges, but it also competes with the water. It absorbs the water so much. So then what we were thinking was, if we use this PIMS as a surface, it can let CO2 in, but at the same time, maybe reject the water. And that's what we start working on. So we actually make these materials. So on the top left, you can see that we put gnomes as a core solution. It's similar to how we did the microfluidic device with the droplet inside droplet, but shell material is not UV cured. It's a solvent evaporation. As evaporating solvents, polymer becomes a fiber. And we were able to embed a lot of gnomes, and it worked pretty well on CO2 capture as well. So finally, how would you combine CO2 capture and conversion? Because we talked about not only making construction materials, but all the chemicals as well. But one of the things was we always started with captured carbon dioxide. And if you look at the CCS, they always had carbon capture as you capture CO2 at high concentration, and then they compressed it on around 150 atmospheric pressure, because they always assume that they're going to inject into the geological formation. But that's really expensive. But if we are making something else, like what if we are using CO2 as a feedstock for making ethanol? Maybe we don't need 150 bar of pressure. So people start to think that if you combine CO2 capture to utilization, maybe we should not have the same target. And then we can lower the carbon capture cost. So people start really looking into this. So one of the first things people start thinking about was CO2 is really low in energy level. We can make jet fuel out of CO2 if you want to. We can make ethanol, we can make plastics, all that. But we need the carbon-free energy to move upwards, right? So if I burn coal to convert CO2 to plastics, that doesn't make sense, right? Because the coal burning emits the CO2, so the overall net CO2 not going to be benefit. So then we were waiting until we have a carbon-free energy to do all this transformation. And apparently we do have it. So now wind and solar energy penetration into the grid is faster than we thought. This is doing really well. Now we need a better catalyst to put all these components into the system and make the stuff we want. But one last thing is, remember, carbon dioxide has only carbon and oxygen. We need hydrogen somewhere to make materials and fuels. So there's a lot of questions now, and this is one of the reasons we had energy earthshot, first one on hydrogen. So hydrogen has many different colors. Did you know that? It doesn't, but we have now color-coded them. So there is a black one, gray one, blue and green, and there's turquoise and new color coming up every day almost. So which one do you think has the lowest carbon intensity? This one seems to be good, right? So this is a splitting water and the low carbon intensity as long as that energy came from renewable energy. So even if you split the water to make hydrogen, if you use the electricity produced by burning coal, that won't be green. You'll be black. You understand that? So the color coordinating hydrogen is all about carbon intensity. So it doesn't, not only it matters whether it came from water or coal or natural gas, but also where energy came from and what happened to the carbon emitted during the transformation is very, very important. So people start looking into, okay, if I want to convert CO2 already capture into something useful, you need to do a lot of study. I'm not going to go into this too much. There's a catalyst design and all that, but what we are really interested in was electrolyte design. You can electrochemically rip off the oxygen from carbon, CO2, and then you can make a lot of interesting things. You can make carbon monoxide, you can make formate, formic acid, and all that so on. But not that many people really studied on how to make electrolyte to do all these reactions. So we went back to NOMS, and we knew based on Lyndon's work that this can be ionically conducted. So if you look at left and right, left-hand side is NOMS mixed in with water. Right-hand side is polymer mixed in water, and we added a little bit of salt as a supporting electrolyte. And we thought, well, if this material works really well for CO2 capture, it can behave well as electrolyte for CO2 conversion. It would be great. So then we tested it. And then if you look at the top left, basically we thought that the polymer will do better, lower viscosity and higher conductivity was what we expected. But it was exactly opposite. So we were getting really confused. Why? And we went back to the lab many times because it was too good to be true. And what we found out was we were getting a wrong picture. So in fact, that NOMS, instead of looking like this, there was some kind of hierarchical structure. So that internally within fluid, there was a different structure was forming, leading to different transport behavior. So we took this to Argonne National Lab, and without going too much detail, since you guys are not familiar, this is the inverse of the length scale. So when you talk about nanoscale materials, at the high Q range, you'll see a lot of signals. That's natural because there's a lot of nanoscale materials. But at the low Q range, you should not see any signals. But you see signals right there, light blue box. This kind of tells you that although I didn't create it that way, there's some chunkier stuff in your fluid. That's what it means. So going back there, we realized that in the zoom in picture, in the naked eye, it looks like a homogeneous, very you see with your eyes. But zooming in, there was and aggregates. And because of that, its transport behavior was really different. So finally, using that, now we just put it into electrochemical cell. And we were able to capture CO2 directly into this conversion reactor. You can see that without our NOMS versus with NOMS, there's a huge boost, right? And we were able to start to make product directly onto this. And in fact, the NOMS does two different things, not only boost up the CO2 concentration in an electrochemical cell, but also they're kind of holding on to this CO2 just right, so that on the surface of the catalyst, so that CO2 is a little bit bent. and it becomes a little more reactive in a kind of unique way. So we were able to use NOMs as almost like a cold catalyst, and we can change the product distribution. So in summary, I think we need to really thinking about multifaceted approach for carbon management for sure. And understanding with the fast integration of renewable energy into our grid, we need to really think about how to get chemicals and materials and fuels using carbon capture and renewable penetration into the system together. And reactive separation is really key for the future for overall sustainability, but I want you to think about not only new pathways to existing chemicals, perhaps we should think about new pathways, new chemicals. Because instead of a petroleum, which is highly reduced carbon, we'll be using a lot more oxidated CO2 or biomass for the future. And at the end, I think you guys are in this program because you care about the earth and the environment. Technology should be developed, keeping the earth and environment within our system boundary. And these are my students and acknowledgement, and I'll be happy to answer any questions. Thank you. Any questions? Yes.
Thank you so much. This was very inspiring. This thing with combining waste from construction of some kind with captured CO2, how long till your connection would you? How much time do you think?
Until we get there in terms of, so the question from the student is combining CO2, capture CO2 with the solid waste from industry to make construction material, how fast we can get there, right? We're already there. So technology has been already commercialized. So I don't know whether some of you know, there is something called 45Q. That's a tax credit in the United States. We already started this. So for per ton of CO2, you get about $35 to $50 per ton of CO2. It justified a lot of this transformation. So there are a lot of startup companies doing this, but not in the large scale yet. One of the reasons is that when you introduce like a new concrete, for example, if it is a road field, no problem, right? Because there's no safety issues. But let's say we are building skyscraper, right? Now we need to make sure that this newly developed material is performing same way, safe, same way. So there's a lot to be done to certify this new material. Same thing with the jet fuel. If you make new jet fuel, you need to make sure that it will perform well at that altitude, right? So there's many steps to make sure that we can find a protocol, how to make them, but also how to test them to make sure that they'll be performing well. I think that bottleneck is needed, like before we have a full deployment of this. But good question. Yes.
That like Nova shut down in 2020. Like I was wondering if there was any other like large scale projects that are now being like run off because of that project.
Sure. So the question is, Petronova project stopped 2020. Is there any other large scale demonstration? So first demonstration in North America was in Canada. So it's a boundary dam project. It was before Petronova project. That one is still going on. There are many smaller projects in many parts of the, not only United States and rest of the world. I think Norway does a lot of them and all that. It's really depending on what you do with capture CO2, because you don't want to do catch and release into atmosphere. So they're usually tied to either storage or utilization projects. And I think the one in Canada is also doing enhanced oil recovery. They haven't stopped their project yet. The one in Norway is injecting into aquifer, they are storing. So depending on, but in the United States, somehow or other, I guess Petronova project stopped because the oil price, but you will go back up, I'm sure, and then we'll do more of that. Yeah, there are many projects. Yes.
So when you were talking about like direct air capture, is there like certain locations? I know it's like solar panels, like maybe areas that get off sunlight. Is there certain areas that have like higher concentration of CO2, like I don't know, like different altitudes or something that would be more efficient to be direct air capture?
Good question. So the question is similar to solar PV, is there a certain location direct air capture is more beneficial, right? Or a good place to put it. So if it is really humid, people usually don't like it because the materials love CO2, also loves water. So unless we circumvent that property, like what we are doing, rejecting water while capturing CO2, you'll be stuck with that. More water is loaded on during the regeneration, you have to evaporate all that water. So energy requirement goes up. So people usually like to do it in Arizona. There's a lot of CO2, but no water kind of issue. But we're not going to do it only in one location. One of the benefits of direct air capture is you don't need to be where point source of CO2, right? So we didn't talk about this class today, but then one of the big thing about capture and storage is the transportation. The reason we compressed it at 150 atmospheric pressure is a pipeline pressure. So then if you can eliminate all that pipeline, wouldn't it be great, right? Because that costs a lot of money and then space and all that. So usually people argue that direct air capture system should sit on top of the storage site or utilization site. I think there will be more geared towards that, so they minimize the infrastructure. But people are now starting to really looking into, can we capture CO2 from sub-zero ambient versus really high temperature? Yeah, there are many spaces. But one thing is farmers did complain. If you put a lot of direct air capture in a row, you deplete the CO2 so much that your crop yield goes down. Kind of interesting byproduct of the having too many. So in a sense that you have to, similar to wind farm, you have to space them out. So there's a lot of atmospheric modeling happening, how far they should be and where they should be. Kind of interesting, like a solar farm. Yes?
In follow-up to that question, you're talking about the externalities how farmers can make their most part of the year for their crops, but like, were there environmental studies done on just the area itself as like the drilling that has to be done in order to get
You're talking about carbon storage, for example, right? Environmental impact of carbon storage. Of course, that's one of the biggest challenges people thought about, because 150 bar CO2 is not low pressure. You're really injecting high pressure. So are we gonna get fracking? Yeah, right? So depending on the geological formation, do we worry about fracking? Yes, right? Is there gonna be any potential leakage? Yes, right? So what is the most important thing? Find the right site, right? There are, but you have to do full characterization. So it's not just because I found a pocket, it does not mean we can inject. Not only that, we have something called monitoring, verification, and accounting. So once you inject CO2, you want that to be staying there, right? So then there is a lot of studying, making sure that it stays where we injected, and then eventually it gets depressurized. But over the year, every year, not only we pay for CO2 capture and storage, but we'll be paying for monitoring over the long period of time. So this is one of the important things. And as I mentioned, if you put that amount of fluid, the fluid which was already there will be pushed outwards, right? Where is it gonna go? Is it gonna contaminate something else? These are all big challenges we have to answer. But if you think about all the natural gas we've been using, petroleum, there's a lot of geological formation we can tap into. We just need to do it very carefully.
So I think it's 4 o'clock. So let's thank Alissa again for coming up.